Let's see the one more problem on the rigid bars. Two horizontal rigid bars AB and CD are connected by two wires of aluminum and copper as shown in figure. Both wires have length of capital L. Vertical loads capital P are applied at midpoints E and F of the two bars. Compute the increase in displacement in the distance between the points E and F when loads are applied. Okay, let's see the solution. And let us consider suffix AL are using for aluminium wire and suffix CM is used for the copper wire. Then extensions delta for the aluminium, that is the delta AL, and extension of the copper wire, that is the delta CU, of the two wires will be the different. Hence the displacement delta between the points E and F is given by delta equal to 1 by 2 into delta AL plus delta CU. See here, extension of the aluminum and copper wires are the different because both are having the different E values, but displacement of the bar should be the average value of the aluminum and copper wire displacement. So displacement of the rigid bar delta equal to the average of the displacement of aluminum and copper. So delta equal to 1 by 2 into delta AL plus delta CU. Let's consider this is the equation 1. Next, from the statical equilibrium, by taking the moments about the plane AC, we will be get P suffix Cu into the AB equal to P into AE. Here PCU is the reaction force generated in the copper wire. Here we are applying the load P on the rigid bar. Then in the opposite direction, reaction forces it will be generated in the aluminum as well as the copper wire. Let's consider reaction force generated in the aluminum wire is the PAL and reaction force is generated in the copper wire is the PCU. First we have to considering the equilibrium condition. Here I have to consider the equilibrium condition from the plane AC. From the AC plane we have to consider the equilibrium. So momentum, here you have to consider the 0. So then we know momentum is the force into the distance. So here, so upward forces into distance equal to the downward forces into the distance. So upward forces is the P and the distance is the AE. So P into AE should be equal to the downward force PCU. So PCU into distance is the AB. So PCU into AB equal to the P into AE. So from here we can be written as PCU equal to the P into AE by AB. Here E is the midpoint between the points A and B. So PCU can be written as 1 by 2 into P. Similarly, we have to considering the statical equilibrium. For this, taking the moments about the plane BD, we will be get PAL equal to the 1 by 2 into P. So next we have to see the deformation in the aluminum wire. We know deformation delta equal to PL by AE. Similarly here, deformation for the aluminum wire delta AL equal to the PAL into L divided by AAL into EAL. So here PAL is the reaction force or applied force on the aluminum wire. L is the length of the aluminum wire. AAL is the cross section of the aluminum wire. EAL is the Young's modulus of the aluminum wire. And we know the relationship is the PAL equal to 1 by 2 into P. And we know AAL is the cross sectional area, that is the pi by 4 d square of the aluminum wire. Then delta AL can be written as 1 by 2 PL divided by pi by 4 d square of AL. So DAL is the diameter of the aluminum wire into EAL. So this can be written as 2PL by pi d suffix AL square into EAL. Similarly, we will be get delta Cu, so that is the deformation in the copper wire, equal to the 2PL by pi dCu square into ECu. So we know the relationship between the deformation of the aluminum and deformation of the copper and the deformation of the rigid bar, that is delta equal to the average of the deformations of aluminum and copper wire. So that is delta equal to 1 by 2 into delta AL plus delta Cu. So we know the delta AL value and also we know the delta Cu value. Then substitute, we will get the delta equal to the 1 by 2 into 2PL by pi DAL square into EAL plus 2PL by pi dCu square into the ECu. So here 2PL and the pi, so let take common and the bring out, so from the bracket, then delta will become the PL by pi into 1 by DAL square into EAL plus 1 by dCu square into ECu. So this is the deformation of the rigid bar. This expression we will be used for the deformation of the rigid bar. So when the two wires are made by the different materials, here we are considering the aluminum and copper. Let's say the another expression, if the both of the wires are made by the same material, if the same material means its Young's modulus also it will be the same for the both of the wires. So if both the wires are of same material, then Young's modulus of the both of the wires should be the same. Let's consider that is the capital E. Then deformation equal to the PL by pi E into 1 by d1 square plus 1 by d2 square. Here d1 and d2 is the diameter of the first wire and diameter of the second wire. So this is the solution, and thank you.